In this video, we will work on this problem from 2025 Advanced Paper 1. So let us look at the thought process. So read the problem and comprehend what is happening overall, and then identify the key point of the problem, right? So if you read the problem, you will see there is a square loop of length L, and that is moving into a magnetic field, right? Moving this way, and the magnetic field is only in the positive xy plane, and the direction of the field is perpendicular to the loop. So as the loop will enter, you should know that in this problem you will have to use Faraday's law of induction, right? As the loop will enter, the magnetic field through the loop will increase, and based on Faraday's law of induction, you will have voltage, you will have current, and because of that current you will have a force that will slow down the loop. So the goal is to check each point if that is correct or not. Read all the options, not the values, to see how they relate to each other, and you will see option A, C and D. Like option A, C and D, they are about like the speed and time, right? And when the loop stops. Option B is about when the loop is completely inside the magnetic field. So this is the figure showing the loop at a time t, right? The yellow area is inside the magnetic field, and the flux through that area is phi, right? And the flux is perpendicular to the area, right? The magnetic field. So we will calculate what is the flux. So flux will be straightforward. You have constant magnetic field B naught, right? And B naught is in Z direction. So you take B naught and multiply that by the area ST. ST is this yellow area, right? That is your ST, and that will give you magnetic flux at time t. And as the loop is entering the field, right, S will change, it will increase. So the rate of change of flux will give you the EMF, Faraday's law of induction, right? So d phi by dt will be B naught L V, because B naught and L are constant, and ds by dt, how fast this S is changing, which is the speed of the loop. Now this voltage will create a current in the loop. As you can see, the current will be I, right? And the current will be like this, because this current will create a magnetic field in the negative z direction, to counter the increase in the flux, right? That is Faraday's law of induction. So what will happen? Because of this current, you will have a force, right, being applied by the magnetic field. Look at this law. Magnetic field exerts a force on a current carrying wire, and the formula is B naught IL, and the field is upward, current is in the x direction, so the force will be in the negative y direction, right? This force in these two segments here and here, the force will be equal and opposite, so they will cancel out. Newton's law. So now see, this force will matter, and that force is this force here, minus B naught IL, right? That will slow down the loop. So F equal to ma will give you m dv by dt. And now if you apply integration, right, so you can do your math, and you will get the velocity is an exponential function, and if you integrate velocity, you will get how this S here, how this S will change over time, right? So let us summarize what is happening. The velocity will reduce exponentially, so the loop will stop at infinite time, the exponentially, and the distance traveled by the loop will also change exponentially, right? And eventually at infinite time, the loop would have traveled V naught by K. But now here is something very interesting. If S is greater than L, then what will happen? If S is greater than L and L is this, then the loop would have entered the magnetic field and something will change. So here, When S is greater than L, the loop will enter the magnetic field completely, like you see here, right? Completely. And in that case, you can see all the forces, they will cancel out, right? Because the force on this side of the loop will cancel the force on this side because of the opposite direction of the current. Look at the current, they are in the opposite direction. So the net force will be zero. So once the loop enters the magnetic field, it will not slow down, and after that it will keep moving with constant speed forever. Now we can look at our options. Option A says V naught equal to 1.5 kL. The loop will stop before it enters the magnetic field completely. And if you put S equal to V naught by K, right, the maximum distance the loop will travel before stopping, and you will see if V naught equal to 1.5 kL, then S is 1.5 L, which is more than L. That means loop will enter the magnetic field. So option A is wrong. It will not stop before it enters completely. Option C, V naught is KL by 10. The loop comes to rest at this time, right? So here's the thing. If you put this V naught here, S equal to V naught by K, you will get S L by 10, which is less than L. That means loop will not enter the field. It will stop before entering the field. If you go back here, right here. So if S is less than or equal to L, it will stop before we get to in this condition on the right side. So that means C is also incorrect. B, when the complete loop is inside the region of the magnetic field, the net force acting on the loop is zero. B is correct. That's what we discussed here, right? Here, that once you enter the magnetic field completely, the net force will be zero because of the currents cancelling each other, right? The force on different parts of the loop. And now the last part, D, it says if V naught is this, at what time the loop will enter the field. So you just put S equal to L, S equal to L, and you have to find out what is time, right? And you do your calculation, you will get T equal to 1 by K logarithmic 3 by 2. So D is also correct. So the most important thing is to understand this portion, that this is for this portion here is S less than or equal to L, right? And this portion on the right is S greater than L. S less than or equal to L means that V naught is less than or equal to KL. Then the loop will never enter the magnetic field, right? And if V naught is greater than KL, then the loop will enter the magnetic field.